The subject we want to consider today is chemistry, and under it we are looking at thermodynamics. Of course, it is not a new concept to you, but we just want to do justice to it. Thermodynamics in its real self is a very large topic in science, whether physics or chemistry, but we just want to narrow our discussion today to three particular aspects. We want to talk about the enthalpy of a reaction, we want to talk about the entropy, and then we want to talk about the Gibbs free energy of a reaction. So what is thermodynamics? It's just the relationship between heat and other forms of energy. Then, as we said, we want to look at enthalpy. Enthalpy is the heat content of a system, the heat contained in a chemical reaction. So, and then it could be of two types. We could have it as positive. It is positive when the heat content of the product is more than that of the reactant. That type of reaction, we call it an endothermic reaction, where it is absorbed from the environment. Then it could be negative. In this case, the heat content of the product is less than that of the reactant. Then we call this type of reaction an exothermic reaction, that is, heat is given off to the environment. Then for the entropy, entropy is the degree of disorderliness of a system, while Gibbs free energy is what tells the predictability of a reaction, whether a reaction will proceed or not. So Gibbs free energy also could be positive. If it is positive, we call it a non-spontaneous reaction. That is a reaction that cannot occur on its own, that needs to be inhibited before it reacts. If the Gibbs free energy is negative, we call it a spontaneous reaction. These are the reactions that can occur on their own. They don't need anything before they occur. Then the G could be 0. In this case, we call it an equilibrium reaction. So it is now possible for us, if we have a reaction system like this one, it is possible for us to calculate the standard enthalpy change. So if we want to calculate the standard enthalpy change of this reaction, for instance, we want to see the overall enthalpy change so that we can determine whether it is endothermic or exothermic. All we just need to do is to have a balanced reaction, then have this system. The standard enthalpy change is actually equal to the sum total of the enthalpy of the product, as it is stated here, minus sum total of the enthalpy of the reaction. So if at the end of the day the result is negative, we say it is an exothermic reaction. And if at the end of the day the result is positive, we say it's an endothermic reaction. We can also get the standard entropy change of a chemical reaction. Just like we advised for the enthalpy, the reaction must be a balanced one. So the standard entropy change of a chemical reaction is also the sum total of the entropy of the product minus that of the reactant, as it is stated here. Then we can also get the standard Gibbs free energy change of a reaction system. After we have got a balanced equation, the standard Gibbs free energy change of that system is the change in the Gibbs free energy of the product minus that of the reactant, as we have stated in this equation here. Then to now calculate the Gibbs free energy of a particular reaction system, because we said that is what dictates the predictability of a reaction, there are three ways we can calculate that, as we have listed here. We have this first equation. The Gibbs free energy change can be calculated using this first equation. Change in standard enthalpy change minus temperature times the standard entropy change. But this temperature must be in Kelvin, and also the unit of enthalpy and that of entropy must agree. Enthalpy is in joule, it could be measured in joule per mole or kilojoule per mole. If enthalpy is expressed as joule per mole, we should ensure that that of entropy should also be joule per mole per Kelvin. And if it is expressed in terms of kilojoule per mole, that of entropy should also be kilojoule per mole per Kelvin. That is the first one. We can also calculate the Gibbs free energy using this second equation. This one involves the standard electromotive force, the change, and Faraday constant, the number of electrons involved in the reaction. So this N is the number of electron, F is the Faraday's constant, which is 96,500 coulomb per mole. Then this is the electrode potential of the system. We can also calculate Gibbs free energy with this last equation. Using this equation, dG equals minus RT ln K. R is the molar gas constant, T is the temperature in Kelvin, then the natural ln of the equilibrium constant. K is the equilibrium constant. We just take the ln of it. So with all of this said, we want to take some questions to justify all that have been said so far. The first question states that calculate Roman figure 1, the standard enthalpy change, for Roman figure 1, then Roman figure 2, the standard entropy change, and Roman figure 3, the standard Gibbs free energy change at the temperature at 10 degrees Celsius for the reaction. This is the reaction So what we are asked to calculate 3 things: the standard enthalpy change, the standard entropy change, and the standard Gibbs free energy change for this at 10 degrees Celsius for this reaction. And they give us the standard enthalpies of each of the components of the reaction. For the standard entropy of ammonia, standard entropy of ammonia gas is given as 192 kilojoule per mole. Then the standard entropy of oxygen gas, is given as 205 kilojoule per mole. The standard entropy of nitrogen gas, is given as 191.6 kilojoule per mole, while that of water, gaseous water, is given as 188. It's actually given in terms of joule per mole per Kelvin, everything. So the standard entropy of ammonia, 192 joule per mole per Kelvin, that of oxygen, 205 joule per mole per Kelvin, that of nitrogen, 191.6 joule per mole per Kelvin, and that of gaseous water, 188 joule per mole per Kelvin. So they gave us that of the enthalpy change of each of the components too. That of ammonia is given as minus 80 kilojoule per mole. That of oxygen is 0. That of nitrogen is also 0, while that of gaseous water is minus 242 kilojoule per mole. So we can proceed with our solution now. Don't forget, the first thing we are asked to calculate is the standard enthalpy change for the reaction. To get the standard enthalpy change for the reaction, we have that will be the sum total of the energy change of nitrogen, that is in the product side, times the molecularity, plus that of gaseous water minus enthalpy change of ammonia times the molecularity plus that of So from the data given above, the standard enthalpy of nitrogen is 0. So 2 times 0 plus that of gaseous water is minus 242 minus that of ammonia is minus 80 plus that of oxygen is 0. So we can have it as, let me punch the calculator, 6 times 242. 0 minus 1452, then minus, this is minus 320 plus 0. All right, 0 minus 1452, that's minus 1452 minus 320 plus 0 is minus 320. So we have it as minus 1452 plus 320. So that will be minus 1132 kilojoule per mole. So that will be the standard enthalpy change for the reaction. So using the formula, one of the equations that we refer to initially. So we have got that of our enthalpy change. So we can proceed to calculate for the entropy change. So I will write our answer here. In case I want to rub this part of 132 kilojoule per mole. So let's calculate for the second one, the standard entropy change. For the standard entropy change of the reaction, we have standard entropy change to be 2 times standard entropy change of nitrogen plus 6 times standard entropy change of gaseous water minus 4 times standard entropy change of ammonia plus 3 times standard entropy change of oxygen. So let's input our values there. This entropy change for nitrogen is 192. So 2 times 192 plus that of gaseous water is 188. 6 times 188 minus, for ammonia, okay, for nitrogen is 191.2, 191.6, 191.6. Then for ammonia 192, so 192, then plus 3 times for oxygen 205. So let's punch our calculator. 2 times 191.6, that is 383.2. 383.2 plus 6 times 188, that's 1128. 1128. Then minus 4 times 192, that's 768 plus 615. So adding this together, 1383. This one will be 1383. Then 383.2 plus 1128. That's 1511.2. So if we subtract that, then minus 1383. So our final answer is 128.2. Don't forget, our entropy is in joule per mole per Kelvin. Joule per mole per Kelvin. So, following one of the equation stated above, we've been able to get the change in entropy, which is the second one we are asked to get. So, let me write it here. Change in entropy is 128.2 joule per mole per Kelvin. So the third one we are asked to calculate is the change in Gibbs free energy. But we're not given the individual Gibbs free energy of the components. So we are going to refer to one of the equations that we highlighted before. One of the three ways that we said Gibbs free energy can be calculated. We said Gibbs free energy can be calculated using this equation because we know them. But our temperature had to be converted to the Kelvin. So in converting it to Kelvin, we had from degrees Celsius, we had 273 to it. So that would be 283 Kelvin. Straightforward. We'll just have to substitute our value. But I mentioned something earlier that the unit of enthalpy and entropy must agree. So if we choose that it should be in kilojoule per mole, that means we should ensure that our entropy too is in kilojoule per mole. But if we choose that it should be in joule per mole, we should ensure that our enthalpy is in joule per mole. So if we want to make everything to be in joule per mole, that means we need to change our enthalpy to joule per mole. Better still, let's change our entropy to kilojoule per mole, 128.2 joule per mole per Kelvin. So it will be 0.1282 kilojoule per mole per Kelvin. So what I did was to divide it by 1000, so it will naturally give me be expressed in kilojoule per mole per Kelvin. So we can now go and calculate our change in free energy. Don't forget, the equation we want to use is change in enthalpy minus temperature times change in entropy. So what's the change in enthalpy? Minus 1132, then minus the temperature change is 283 Kelvin times the entropy change 0.1282. That will be minus 1132 minus 283 times 0.1282. So this will give us 36.28. So 1132 so finally our answer will be minus 1168.28 kilojoule per mole. So the standard enthalpy change, Gibbs free energy change for that chemical reaction will be minus 1168.28 kilojoule per mole. And what will that tell us? That it is a what? Spontaneous reaction. So I believe with this example we have given, even though we have plenty example on it that we can take, but for the sake of this class, we are taking this example only. So you can visit some other resources. You can also visit our Facebook and then get more questions and solutions to the topic. Thank you very much.